June 13, 1944, over the skies of southern England, the air was heavy with the expectation of peace or at least respite. The capital had survived the worst. For 3 years, Londoners had grown accustomed to a different type of war, one defined by the predictable though terrifying rhythm of the conventional night blitz. That struggle had peaked, faded, and seemed now relegated to the historical memory of 1940 and 1941. Normandy had been secured just a week prior, and the national mood, though cautious, was buoyant. People were moving out of the shelters, planting victory gardens, and allowing themselves the luxury of looking forward. The danger, they believed, lay across the channel, not above their heads. Then they heard it. It was not the familiar, throbbing drone of the Heinkel bomber, nor the high whine of the attacking Messerschmitt. This sound was mechanical, relentless, and utterly new to the battlefield, a persistent, buzzing rattle like a gigantic motorcycle tearing through the upper atmosphere. It possessed a crude energy, an almost insect-like tenacity, and the sound alone immediately stripped away the fragile sense of post-blitz safety. This was the Pulsejet, the propulsion system for the FZG-76, the German Vengeance Weapon 1, and it inaugurated a new epoch of terror in modern warfare. The weapon itself was anonymous, a small, stubby aircraft with no pilot, just a massive charge of high explosive mounted in its nose and rudimentary guidance determined by an internal gyroscope and a small propeller counting air miles. It was Germany's answer to their failure in the air war, a brute force instrument designed to strike fear and break morale without risking a single Luftwaffe pilot. Londoners quickly nicknamed it the Doodlebug or the Buzz Bomb. But the real terror of the Doodlebug was not the explosion, destructive as it was. The psychological horror was woven into the mechanics of its flight. The sound of the engine, the raucous chatter of the Pulsejet, provided a warning. If you heard the buzzing approaching, you had a brief moment to dive for cover. Everyone in London soon learned the horrific rule: as long as you heard the engine, you were safe. It was only when that rhythmic buzzing abruptly stopped, when the fuel supply was exhausted and the mechanism tumbled into a final, silent dive, that you knew the bomb was falling and you were likely its target. The silence lasted only seconds, but those seconds were eternity compressed, pregnant with absolute, arbitrary doom. You could hear the sudden drop in pitch, the air rushing over the wings, and then the inevitable, shattering impact. Unlike the targeted bombing of the Blitz, where industrial zones or dockyards were the focus, the V-1s were inherently inaccurate. They were launched from ramps across the Channel and simply aimed at the general vicinity of Greater London. The technology, revolutionary as it was, the first true cruise missile lacked any means of precision targeting. It was a terror weapon by design and by technical limitation. It killed indiscriminately, leveling houses, churches, and crowded markets with equal impunity. In just 3 months, beginning that summer, over 9,000 of these missiles would be launched toward the Allied coasts, the vast majority aimed squarely at the heart of Britain. The Blitz may have ed, but for the people of London, 1944 brought a deeper, more unsettling dread, the constant awareness that above the city unseen and utterly arbitrary, the relentless buzz of death was waiting for its terrifying moment of silence. June 13, 1944, deep within the secrecy of the Peenemünde Army Research Center, a new era of conflict was born, though few in the Reich truly understood the nature of the weapon they had just unleashed. This device, officially designated the Fieseler Phi 103 and quickly nicknamed the Doodlebug by the Allies, was in fact the progenitor of modern aerial warfare, the world's first operational cruise missile. It was fundamentally different from a piloted aircraft, a conventional bomber, or an artillery show. The V-1 was an unmanned, pre-programmed vehicle, flying at speeds previously unheard of for a pilotless machine, carrying an almost metric ton of high explosive. For the German leadership, the V-1 offered a solution to the insoluble problem of Allied air superiority. With the Luftwaffe decimated and German cities pulverized nightly by the RAF and the USAAF, the ability to strike back without risking trained pilots was a profound military advantage. This was the ultimate Vergeltungswaffe, the vengeance weapon long promised by Hitler to reverse the psychological and material damage inflicted by the Allied bombing campaign. The missile's existence allowed the Reich to strike directly at the enemy's morale and industrial centers without having to first win back the skies over the English Channel. Its propulsion system was crude but viciously effective, the Argus Pulsejet. This mechanism required initial acceleration via a powerful steam catapult, but once airborne it delivered the distinctive, pulsating roar that became the literal soundtrack of fear for millions in London and southeastern England. It was this unnerving sound, followed by the terrifying silence as the fuel supply ran dry, that defined the V-1 experience. The system of guidance was simplistic, a necessary limitation given the constraints of 1940s technology. Using a basic magnetic compass and an internal gyroscope to maintain a general direction, the V-1's range was governed by a small airlog propeller countermounted on its nose. Engineers calculated the precise number of revolutions needed to reach the target area, usually the densely populated area south of the River Thames. Once the counter reached zero, a mechanism activated, locking the elevators down, sing the missile into its terminal, supersonic dive. This method of operation redefined strategic thought. It was war by automation. The V-1 removed the human element entirely from the attack phase. The victim faced an implacable, tireless machine launched anonymously from dozens of miles away, bypassing defensive fighters and flak concentrations with relative ease. This technological leap, however rudimentary, foreshadowed the post-war ICBM race and fundamentally altered the relationship between distance, defense, and destruction. No longer did geography guarantee safety. Mass destruction could now be delivered by rote mechanism. However, in achieving this strategic terror, the V-1 revealed its primary and crippling limitation: precision. Because its guidance was based on simple timing and fixed direction, a method called area bombing, it could reliably hit London, but not a specific dockyard, power station, or military headquarters within London. The V-1 was a tool of indiscriminate scattergun destruction. It was incapable of the surgical strikes necessary to cripple war production or dismantle military command structures. Its tactical value was almost non-existent. Its strategic value rested entirely on terror and the disruption of civilian life. This inherent failure of accurate targeting meant that the world's first operational cruise missile remained a weapon of psychological warfare, lacking the surgical capability that the German High Command desperately needed to turn the tide of a rapidly losing war. This deficiency would only be partially remedied by the weapon's terrifying successor, a ballistic marvel that sought not just to terrorize but to destroy specific targets from the edges of space. The location for this unparalleled ambition was the isolated Baltic spit of Peenemund. It was here, sheltered from Allied reconnaissance and bombing raids for a time, at least that General Walter Dornberger and his young chief designer, Werner von Braun, led thousands of scientists and engineers in a race against time and gravity. Their focus was Project Aggregate, specifically the A4 rocket, which the propaganda machine would soon christen Vergeltungswaffe Zoe, or V2. Unlike the slow, buzzing V-1, which utilized a relatively simple Argus Pulsejet and flew at altitudes easily accessible to fighter aircraft, the V-2 was pure liquid-fueled rocket technology. It demanded extraordinary engineering precision, burning a volatile mixture of liquid oxygen and alcohol, generating 25 tons of thrust. This energy was designed to propel a 1-ton warhead 50 miles high into the Earth's upper atmosphere before it plunged back down toward its target at speeds exceeding 3,600 miles per hour, nearly 5 times the speed of sound. This velocity was the V-2's most terrifying feature and its greatest tactical advantage. It meant the V-2 struck without warning. There was no audible signal, no time for sirens or air raid shelters, and no defense. The blast was the first indication that the weapon had arrived. This capability fulfilled Hitler's desire for a weapon that was not merely destructive, but completely unstoppable, shattering civilian morale in Allied capitals. The project itself, however, had been slow and immensely costly. Plagued by exploding prototypes, engine instabilities, and internal political squabbles within the fragmented Nazi bureaucracy. Initial testing began as early as 1942, but it was not until the devastating Allied bombing raids on German cities intensified in 1943 that the Führer truly threw the state's massive, albeit strained, resources behind the rocket program. Hitler, desperate for a decisive counterblow and increasingly convinced of his own techno-utopian vision, bypassed traditional procurement channels and granted Dornberger and von Braun virtually unlimited priority status. The engineers at Peenemünde suddenly commanded the material and manpower required to transition the massive rocket from a theoretical physics problem into a practical weapon of war. The pressure from the high command was constant and crushing. They demanded immediate deployment, believing the V-2 could shatter the resolve of the British populace and complicate the impending Allied invasion. The engineers, meanwhile, struggled not only with the complex physics of guided rocketry, but also with the increasingly dire logistical reality of manufacturing sophisticated components, while Allied air superiority chipped away at the German industrial base. Peenemünde grew from a research laboratory into a vast military-industrial complex. Leveraging thousands of forced laborers, mostly political prisoners, and captured Soviet soldiers to realize the ambition of the world's first true ballistic missile. The genesis of spaceflight was inextricably linked to the final, panicked desperation of the collapsing Nazi regime, driven by the belief that ultimate technological supremacy could still reverse strategic defeat. By the summer of 1944, as Allied forces landed in Normandy, the V-2 was finally deemed operational, though reliability remained a persistent issue. The shift from experimental launches to mass bombardment required an entirely new infrastructure. Mobile launching units capable of concealing themselves quickly and a dedicated, ruthlessly enforced manufacturing base housed deep underground, safe from Allied eyes and bombs. This transition moved the primary production of the V-2 away from the Baltic coast and into the massive subterranean tunnels of the Mittelwerk facility near Nordhausen. There, in the dark, cold confines carved out of the Harz Mountains, the true human cost of the V-weapons program was exacted, fueling Hitler's last great technological gamble. This technological fixation, however, was not limited solely to the colossal, complex engineering required by the A-4 rocket, better known as the V-2. Hitler's arsenal of retribution also contained the Vergeltungswaffe 1, a weapon based on an entirely different premise, the pilotless flying bomb. While the V-2 sought to utilize extreme altitude and supersonic speed, the V-1 was a marvel of murderous economy, propelled by an engine that remains one of the most distinctive sounds of the Second World War. This sound, the rhythmic, deafening rattle that earned the V-1 the universal nickname Buzz Bomb, was generated by the Argus As-Aero 4 Pulsejet engine. Compared to the massive, intricate pumps and precision nozzles of the V-2's liquid-fueled rocket motor, the Argus was simplicity itself, a 9-foot steel tube that looked, deceptively, like little more than a crude stovepipe. Its design was revolutionary because it was air-breathing, operating continuously as long as the missile maintained a minimum forward speed. The propulsion depended entirely on a simple yet ingenious mechanical cycle. At the front of the Argus tube were banks of spring-loaded flap valves, often called louvers. The V-1 had to be accelerated rapidly off its launch ramp to ensure enough airflow to start the process. Once launched, air rushed into the combustion chamber, slamming the louvers open. Fuel, typically low-grade gasoline, was injected and ignited, causing a small, powerful explosion. The rapid pressure increase from this combustion immediately slammed the fragile flap valve shut, containing the explosive force and directing the exhaust gases powerfully out the long rear tube, generating thrust. As the exhaust exited, the pressure inside the tube dropped rapidly, creating a vacuum that instantly pulled the spring-loaded louvers open again. This allowed a fresh charge of air to enter, restarting the cycle. This process: air in, fuel injected, valves shut, explosion, exhaust out, valves open occurred with astonishing speed, typically around 45 to 50 times every second. This rapid sequence of small, controlled internal explosions created the Argus engine's signature sonic fingerprint, a furious, relentless drumming sound that could be heard approaching for miles, often long before the V-1 itself became visible. Crucially, the Pulsejet required no complex moving parts other than these simple valves. There were no pistons, no turbine blades, and no gearbox, making it incredibly cheap and fast to mass produce, perfectly fitting the Nazi regime's desperate need for sheer volume. The downside to this mechanical simplicity was twofold. It offered zero throttle control, meaning the V1 flew at a constant maximum speed dictated by the engine's current performance, and more significantly, the flaps eventually failed due to heat and vibration, giving the missile a finite flight duration. For the terrified population beneath, the true terror of the buzz bomb lay not in the explosion itself, but in the sudden, abrupt silence. When the Argus engine ran out of fuel, or when its internal timer commanded a dive, the combustion cycle ceased. The distinctive buzz would cut out, replaced by an unnerving and complete silence that signaled the missile was now gliding toward the ground, offering the few seconds of agonizing dread before the 1-ton warhead impacted. This terrifying countdown was the deliberate psychological component of the V1. While the V2 was too fast to offer warning, the V1's audible approach was an instrument of psychological warfare, making the Argus engine perhaps the most recognized and feared propulsion system of the war. Its technical limitations, however, were immense. Without complex guidance systems, the Pulsejet could only be aimed crudely, making it a terror weapon, but never the precise battlefield instrument German High Command needed. The engineers responsible for transforming the Pulsejet into a viable weapon system recognized that the airframe itself had to be a masterpiece of ruthless efficiency. They were designing not an aircraft, but a disposable projectile, capable of carrying a massive warhead while being cheap enough to produce by the tens of thousands. The mandate given to Feisler Flugzeugbau, led primarily by design architect Robert Lusser, was simplicity above all else. This dictated every choice, from the material palette to the aerodynamic configuration. The initial mock-ups faced immediate logistical hurdles. By 1943, Germany's strategic material reserves, particularly high-grade aluminum, were severely strained. The Phi 103, their Probe-T-Vine, therefore, could not rely on traditional aircraft construction. Lusser and his team pivoted, developing an airframe heavily dependent on steel stampings, easily available sheet metal, and non-critical materials like plywood for the wing spars and leading edges. This commitment to inexpensive, abundant resources allowed for rapid subcontracting and assembly line production, a crucial step in fulfilling Hitler's desire for a massive retaliatory bombardment campaign. Aerodynamically, the design was deceptively straightforward. The fuselage was a thick, cigar-shaped cylinder, housing the fuel tank, initially 70 gallons of gasoline, the warhead, and the rudimentary guidance system. The wings were positioned high on the body, a configuration chosen not for maximum lift efficiency, but for ease of manufacture and structural rigidity around the main fuel bladder. These stubby, high-aspect ratio wings allowed the missile to achieve a reasonable subsonic cruise speed of around 400 miles per hour, but they introduced challenges in stability, especially when launched from the ground catapults or dropped from aircraft. The chief aerodynamic problem lay in controlling the flight path across long distances without the benefit of complex computers or human intervention. The V1 had to maintain a straight course in turbulent atmospheric conditions, propelled by a thrust mechanism that vibrated violently. The solution was the autopilot package, a miracle of wartime miniaturization that was simultaneously the missile's greatest strength and most profound weakness. This package comprised two core components: an altitude sensor that kept the missile at a preset height, typically around 2,000 feet, and a sophisticated Anschutz gyroscopic stabilization system. This gyroscopic system countered the yaw and pitch caused by crosswinds and engine pulsations, keeping the missile nominally on the trajectory set before launch. However, steering relied on a very simple magnetic compass. While effective for setting a general direction, this system was notoriously vulnerable to magnetic anomalies, strong electrical interference, or, more commonly, the accumulated mechanical slop of a mass-produced mechanism. Deviations of several degrees were common over the course of the 150-mile flight path across the English Channel. Furthermore, the range determination was entirely mechanical, relying on an airlock, a small propeller mounted on the nose that measured total accumulated air mileage. Once the predetermined number of revolutions was reached, a small linkage severed the control connection, putting the missile into a steep, unrecoverable terminal dive. This mechanism ensured the missile would eventually fall, but offered absolutely no correction for external factors. If the missile flew into an unexpected headwind, the air log would undercount the true ground distance traveled, causing it to fall short. If it was propelled by a strong tailwind, it would overshoot the target area entirely. The engineering brilliance lay in the elegant integration of these crude systems into a highly stressed, yet mass-producible structure. The engineers mastered the art of the 99% solution, a weapon that was reliable enough to launch and reach the general target area, but fundamentally incapable of achieving the precision necessary to destroy hardened military targets or specific industrial complexes. This inherent limitation cemented the V-1's reputation not as a strategic weapon of surgical strike, but as an inescapable expression of indiscriminate terror. The speed of design was prioritized over the accuracy of execution, resulting in an airframe that was cheap, fast, and devastatingly inaccurate. January 29, 1945, 2 p.m. at Peenemünde Army Research Center. The rudimentary guidance system that steered the V-1 across the English Channel was a triumph of minimalist engineering, but simultaneously a profound failure of strategic precision. It hinged upon an inexpensive, air-driven autopilot that was linked mechanically to a primitive magnetic compass and a compact, sensitive pitch-and-roll gyroscope. Once the initial trajectory and altitude were established on the launch ramp, this simple system's sole purpose was to maintain that straight, level course until the missile reached its pre-calculated destination point of feet that proved consistently impossible over extended ranges. The gyroscope, the indispensable heart of the V-1's directional stability, was ironically the source of its most persistent error. Unlike the extremely expensive and complex inertial units being developed for advanced German rocketry, the V-1's unit was designed for rapid mass production, emphasizing cost efficiency over uring accuracy. The sustained, violent vibration generated by the Argus Pulsejet engine, combined with rapid and uneven thermal changes encountered as the missile climbed and traversed varying atmospheric layers, caused the gyroscope to suffer from significant drift. This phenomenon, known as precession, meant that even if the missile left the ram perfectly on target, its internal reference point, the true vertical and directional heading, was continuously shifting, introducing subtle but cumulative errors into the flight path. Adding to this inherent instability was the flawed mechanism intended to correct these directional deviations, the magnetic compass. Standard magnetic units are highly susceptible to local interference, yet the V-1's design placed this critical navigational tool directly within a hostile electromagnetic environment. The airframe itself was a tube of ferromagnetic steel surrounding a powerful running engine that generated heat, vibration, and fluctuating electrical signals. The magnetic field created by the missile's own body massively compromised the compass readings. German engineers attempted meticulous calibration exercises during ground setup, aiming to calculate and negate these structural deviations. However, airborne electrical interference, minor shifts in the internal magnetization of the metal over time, and the sheer physical instability of the high-speed platform reread these initial ground corrections temporary and ineffective at best. The autopilot, working from corrupted data supplied by a drifting gyroscope and a magnetically confused compass, was therefore continuously fighting against phantom corrections and accumulating deviations. It could not hold a straight line for long distances. Over the approximate 150 miles of flight from the launch bunkers along the Pas-de-Calais coast to the target zone in London, the accumulated navigational errors stemming from these rudimentary flaws could easily translate into a terminal impact deviation exceeding 10 miles. The consequence was that the V-1 could not be reliably aimed at a specific hardened objective, such as a military headquarters, a key bridge, or a vital power station. Instead of striking specific coordinates, the weapon was fundamentally designed to aim for the center mass of an entire metropolis. The true strategic target of the German High Command was never the exact location of a military installation, but the vast civilian density of the urban area itself. This inherent precision paradox meant the V-1's success metric was not measured by a surgical strike, but by the devastating statistical certainty that it would hit something populated, confirming its place in history not as a strategic marvel, but as an inescapable instrument of indiscriminate terror. November 15th, 1943, near the coastal village of Lottingthon, France. The immense logistical effort required to launch Germany's terror weapons was underway, following Hitler's explicit demand for immediate retaliatory vengeance aimed squarely at London. German construction battalions, the massive organization taught hard, blanketed the landscape of occupied northern France. They were building what Allied intelligence would eventually, and perhaps ironically, call the ski sites. These structures earned their code name because their distinctive launch ramps, when viewed from the high altitude of reconnaissance aircraft, strongly resembled the profile of an enormous ski jump. They were not disposable, quick-use field setups. These were complex, heavily fortified installations designed for rapid, sequential fire, intended to sustain a continuous barrage against England. Each fixed V-1 battery typically required an enormous footprint, incorporating 5 key distinct structures: the 90-foot launch ramp itself, specialized storage bunkers for the volatile fuels, the highly corrosive T-Stoff hydrogen peroxide, and the methanol-based B-Stoffe, dedicated magnetic compass calibration building, essential for setting the gyroscope prior to launch crew barracks, and crucially, extensive approach, roads carefully camouflaged into existing villages or dense tree lines. The Germans spared no expense in trying to disguise the nature of these installations, employing nets, false roofs, and planting young trees over freshly poured concrete. But the sheer scale of the building effort, coupled with the telltale geometric patterns that repeated dozens of times across the Pas de Calais, doomed the camouflage efforts. By late 1943, Allied photo interpreters were raising alarms about the sudden, aggressive patterns appearing in fields just across the Channel. This burgeoning threat precipitated the launch of Operation Crossbow, the overarching Allied military and intelligence effort designed specifically to counter all German long-range weapons, encompassing both the V-1 and the far more mysterious V-2 program. While the exact function of the structures remained ambiguous early on, the scale of the construction necessitated immediate and sustained air attack. The motto became simple: if it looked like a V-weapon site, bomb it until nothing remains. The bombing campaign of late 1943 and early 1944 was relentless, a pre-invasion strategic effort that consumed immense Allied resources. Bomber Command and the 8th Air Force poured thousands of tons of ordnance onto the construction sites. This effort proved highly successful. Allied bombers neutralized dozens of the major fixed launch complexes before a single missile could be operationally fired. Faced with the total destruction of their rigid, static network, the German commanders were forced to rapidly pivot away from the huge concrete ski sites toward a far more elusive deployment model. They swiftly adopted smaller mobile launch platforms known as the Bodenstandiker or Stellung sites. These were ingeniously simple, consisting often of little more than a prepared concrete pad hidden deep in an orchard or a dense patch of forest, served by a light portable ramp assembly like the modified Launch Ramp 1, famously known as the Meilerwagen. This compulsory transition bought the Germans the time they needed. By the late spring of 1944, a vast, decentralized network of hundreds of temporary, easily concealed launch positions replaced the few, heavily fortified ones that had been destroyed. Following the D-Day landings, and with the Allied advance still consolidating its position in the Normandy bridgehead, the order for the first operational launch was given. In the early hours of June 13, 1944, just days after the invasion had captured the world's attention, the long-awaited terror campaign finally began. The first flying bombs screamed toward England, signaling the start of the V-1 offensive and introducing the world to the age of missile warfare. The launches themselves achieved exactly what Hitler had hoped for in one sense: massive psychological impact. London awoke to a terrible new sound, the buzzing roar of the Pulsejet engine, which suddenly cut out, followed by an unnerving silence that meant the bomb was diving toward the Earth. The British quickly dubbed the new weapon the Doodlebug, or the flying bomb. The Germans, meanwhile, extolled the virtues of the Vergeltungswaffe 1, or Retaliation Weapon 1, touting it as the technologically advanced instrument that would bring England to its knees. But beneath the propaganda lay a cold, hard fact of early missile technology. The V-1 was a masterpiece of mass production and raw thrust, but it was an amateur in terms of navigation. Its guidance system was rudimentary, relying entirely on mechanics, making it inherently a weapon of area saturation rather than surgical precision. The trajectory was governed by two basic principles: direction and distance. Direction was controlled by an internal magnetic compass, stabilized by a pair of gyroscopes. This kept the missile generally aimed along its preset azimuth, usually toward the heart of London. However, these gyroscopes were easily thrown off by strong crosswinds or turbulence, causing the V-1 to drift far from its intended line of flight. Crucially, there was no feedback loop. The V-1 could not look down and correct its course based on geographic features. The mechanism for determining when to dive was even simpler. Affixed to the nose of the missile was a small propeller, designed to count the total air mileage flown. This was the flying bomb's odometer. Before launch, ground crews would calculate the precise distance from the launch ramp in France to the target area in London, say 150 miles. The mechanical counter was set to that number. When the propeller had rotated enough times to register the completion of the flight distance, the counter mechanism tripped, detonating small explosive charges that locked the control surfaces into a dive configuration, cutting the engine in the process. This system was the principal reason why the V-1 could obliterate large swathes of housing districts, but could never reliably strike a critical military target like the War Office in Whitehall or the heavily protected munitions factories along the Thames. The circular error, probable the radius within which 50% of the missiles were expected to land, was so vast that attempting to hit anything smaller than a major metropolitan area was an exercise in pure chance. If the wind speeds were higher than anticipated, the missile would reach its set mileage before reaching the actual target area. Conversely, a headwind or weaker pulsejet thrust meant the missile would overshoot, often landing further into the countryside or deep in the suburbs. A variance of even a few percentage points in atmospheric pressure or temperature across the English Channel could translate to a positional error of several miles upon arrival. The result of this technological limitation was strategic terror, not strategic destruction. Between June 1944 and the of the campaign, over 9,000 V-1s were launched against England, the vast majority aimed at London. They killed nearly 6,000 civilians and destroyed thousands of homes, forcing mass evacuations and consuming vital Allied resources in defense. But they failed utterly to achieve Hitler's actual military objective, paralyzing the Allied war machine. Supply lines to the Normandy beachhead continued uninterrupted. Factory production slowed only minimally, and military headquarters remained frustratingly intact. The sheer volume of attacks eventually forced the Allies to alter their defensive strategy, repositioning anti-aircraft guns and fighter patrols in a desperate attempt to create a barrier along the southern coast. In a clever intelligence deception campaign, the British even managed to convince the Germans through misreported casualty figures that the missiles were landing several miles short of the central city. The Germans, attempting to improve their accuracy, adjusted their launch calculations, inadvertently causing subsequent missiles to land harmlessly further south, away from the dense civilian population. The V-1 was revolutionary, proving that an unmanned vehicle carrying a massive warhead could be launched hundreds of miles away. It heralded the arrival of the cruise missile age, yet it was the definition of blunt force, a weapon that could reshape the map of a neighborhood, but which lacked the subtle brain needed to win a war. It was indiscriminate destruction, and it was quickly proving that terror alone was not enough to defeat a resolute enemy. June 13, 1944, 4018 a.m. over Swanscombe, Kent. That was the moment the weapon earned its terrifying moniker, the buzz bomb. It was not the shattering explosion that defined the experience of the V-1, but the preceding journey, the unmistakable coarse drone of the Argus Pulse jet engine tearing across the sky. The engine was the German signature, a sound that drilled into the deepest parts of the civilian psyche. unlike conventional bombs whose arrival was a split second of violence followed by silence. The V-1 gave its victims minutes of warning, minutes saturated with the agonizing question, where will the noise stop? The strategy behind the V-weapons, the vengeance weapons, was never primarily military. It was purely psychological warfare. After the devastating Allied bombing campaign leveled German cities, Hitler was desperate for retribution, seeking a weapon that could inflict visible, widespread chaos on the British homeland and break the morale of the population. The V-1, despite its lack of accuracy, was perfect for this mission. When launched against a target as large and densely populated as London, true precision was irrelevant. Anything hit was a victory for the propagandists. The sheer volume of fire was staggering. Within the first 2 weeks of the V-1 campaign, known to the British as Operation Diver, over 2,000 missiles were launched toward England, while many were shot down by fighters, tangled in barrage balloons, or defeated by sophisticated anti-aircraft fire. Hundreds made it through. They fell indiscriminately on homes, schools, hospitals, and parks. Life under the flying bomb meant constant vigilance. The sound of the buzzing engine signaled danger, but it was the sudden, awful silence, the telltale sign that the fuel had run out and the deadly dive had begun, that truly generated mass panic. Londoners quickly learned that if the sound passed overhead and kept going, they were safe for the moment. If the sound suddenly stopped, the next few seconds were all that mattered. This continuous psychological assault achieved a level of sustained terror that conventional air raids rarely managed. People were not simply afraid of dying. They were exhausted by the anticipation of death. Sleep became a luxury, reserved only for moments when the sky seemed briefly empty of the ominous drone. But the German calculation was flawed. Instead of breaking the will of the British people, the V-1 campaign hardened their resolve, transforming fear into a stoic defiance, buttressed by an ever-improving defense system. As Allied forces successfully pushed deeper into France and Belgium, the launch sites for the V-1s were overrun or destroyed. However, the terror did not cease. It simply moved. Once the crucial logistical hub of Antwerp was captured and operational in late 1944, the Germans immediately retargeted their vengeance weapons, turning the full fury of the V-1 and the far more devastating supersonic V-2 toward the Belgian port city. Antwerp became the most heavily bombarded city of the entire war. The German goal here was slightly more focused than in London, to destroy the docks and paralyze the flow of millions of tons of supplies essential for the continued Allied advance toward the Rhine. Yet, the V-weapons remained blunt instruments. Though some strikes hit the dockyard infrastructure, the majority of the missiles, guided by their imprecise navigation systems, fell wildly short or wide, landing squarely in densely populated residential areas. The attacks on Antwerp were relentless, lasting over 6 months and involving nearly 4,000 separate weapon impacts. Unlike London, which was heavily defed, Antwerp initially lacked adequate anti-aircraft defenses, making it tragically vulnerable. The concentration of strikes resulted in catastrophic loss of life, killing over 5,000 civilians and wounding many thousands more. The strategy was the same: terrorize the population and disrupt essential military operations. But just as in London, the citizens of Antwerp refused to break. They sheltered, they mourned, and they went back to work, ensuring the vital supplies continued to flow, confirming once again that the German engineers had built a marvel of destructive power. But they had fundamentally failed to grasp the resilience of the enemy they were attempting to defeat. The promise of victory through terror had delivered only mass graves and hardened hearts. July 10, 1944, 4 a.m., along the white cliffs of Dover, as the Pulsejet engines of the flying bombs began their relentless intrusion into British airspace, the decentralized, frantic initial response rapidly hardened into a professional, lethal defensive cordon known as Operation Diver. The British defense planners recognized they could not entirely stop the weapons, but they could dramatically reduce their rate of successful penetration into London and the vital southeastern industrial heartland. This required a profound integration of every available asset, turning the English Channel and the coast into a lethal gauntlet. The first line of defense fell to the fighter pilots, predominantly flying the swift Hawker Tempest, the late-model Spitfire, and the P-51 Mustang. These aircraft were fast enough to match the V-1's roughly 400-mile-per-hour cruising speed, but standard interception techniques were often too dangerous. Shooting the missile down conventionally risked detonating the 1,800-pound warhead prematurely, scattering deadly shrapnel that could easily destroy the pursuing aircraft. Furthermore, shooting them down over populated areas merely relocated the lethal impact from a random urban target to a slightly less random suburban one. A highly specialized, terrifying maneuver became the signature tactic, the fighter tipping or winging maneuver. The pilot would approach the V-1 from the rear, placing his own wingtip beneath the short, stubby wing of the German missile. With immense precision and a steady nerve, the pilot would use the lift and drag generated by his own high-speed passage to gently nudge the V-1's wing upward. This slight displacement was enough to upset the sensitive gyroscope that stabilized the missile's flight path, causing the V-1 to yaw violently. Once the guidance system failed, the missile would enter a steep, unrecoverable dive, harmlessly detonating in an empty field or the sea, far short of its intended target. This was the ultimate display of skill and restraint, using aerodynamics rather than firepower to nullify the threat. Behind the fighter squadrons, acting as a low-altitude deterrent, lay the dense fields of the barrage balloons. These static, cable-tethered defenses, deployed primarily south and east of London, were intended to force the low-flying V-1s to higher altitudes, making them easier targets for the coordinated ground defenses. While few V-1s were actually brought down by striking the balloon cables, the sheer density of the deployment meant any missile flying below 3,000 feet faced a significant and unpredictable physical threat. Their true value lay in channeling the attack into the deadly zones prepared for them. The most transformative change in the anti-doodlebug defense was the strategic reorganization of the heavy anti-aircraft artillery. Initially, the AA guns positioned around London had been ineffective, their conventional fuses and slow reaction times unable to cope with the speed of the V-1. Defense planners made the crucial decision to relocate the vast majority of the heavy guns out of the city and onto the coast and estuaries of the Thames. This concentrated fire belt was entirely dedicated to the V-1 threat. This reorganization coincided perfectly with the mass introduction of the American-developed VT proximity fuse, or variable time fuse. Unlike conventional fuses, which required a direct hit or perfect calculation of time, the VT fuse utilized a miniature radar set within the shell to detect when it was in close proximity to the target before detonating. The difference was revolutionary. Suddenly, instead of requiring hundreds of rounds to achieve one hit, the coastal AA batteries began achieving kills with unprecedented regularity. The lethal coordination between radar tracking, coordinated ground fire, and the proximity fuse turned the coastal regions into a zone of annihilation for the incoming missiles. By the peak of the campaign in August 1944, the combined effort of fighters, balloons, and particularly the repositioned, proximity-fused artillery had achieved an interception rate exceeding 70%. The skies over England were no longer solely the domain of German terror, but a proving ground for Allied technological and tactical superiority. The question that lingered, long after the last doodlebug motor sputtered out over the English countryside, was whether the V-1 campaign represented a true innovation or merely an expensive, fatal distraction for the Reich. From the German perspective, the goal was strategic terror and the forced diversion of Allied resources. And in the latter they technically succeeded, demanding the deployment of thousands of troops, hundreds of interceptors, and the expenditure of millions of rounds of anti-aircraft ammunition. Yet, assessing the program strictly through the cold lens of military economics reveals the depth of Hitler's folly. The production of nearly 30,000 V-1 flying bombs required an immense dedication of Germany's rapidly dwindling industrial capacity. Each missile demanded specialized alloys for its Pulsejet engine, highly skilled labor for the delicate guidance systems, and vast quantities of fuel that were desperately needed by the Luftwaffe's conventional aircraft and the Wehrmacht's tanks. The cost in material alone for a single V-1 was significantly higher than manufacturing several conventional 88mm anti-aircraft shells, and the yield of a successful 88mm strike was militarily definitive. The V-1, by contrast, carried a ton of explosive, often impacting non-critical residential areas or rural fields due to its inherent lack of precision. When the bombs did hit critical targets, the effect was localized and recoverable. When compared to the strategic bombing offensive carried out by the Allied air forces, which systematically dismantled oil refineries, ball-bearing plants, and communication hubs, the V-1 campaign amounted to little more than localized property damage and psychological shock. The Reich's investment in the weapons infrastructure, the immense launch sites in France, the specialized transport chains, the massive test facilities at Peenemünde, and the slave labor dedicated to underground assembly plants represented a colossal diversion of resources that could have fundamentally altered the balance of conventional warfare. Consider the opportunity cost. The steel and aluminum used to construct V-1 airframes could have built more Messerschmitt Me-262 jet fighters, aircraft that posed a genuine threat to Allied air superiority. The specialized engineers and physicists dedicated to perfecting the unstable V-1 guidance systems and improving its operational range were unavailable to refine submarine acoustic technologies or to accelerate other crucial defensive programs. Moreover, the logistical burden was crippling. Launching V-1s required securing and operating complex coastal sites, which quickly became priority targets for Allied bombers and saboteurs. Transporting thousands of highly volatile missiles and their complex supporting equipment across a deteriorating rail network, often under constant air attack, added friction and waste to every step of the process. Ultimately, the V-1 killed over 6,000 civilians and wounded 18,000 more. It destroyed approximately 23,000 homes. These were tragic statistics, certainly, but they did not halt British war production. Nor did they force the diversion of critical Allied forces away from the invasion of Normandy, which remained the central strategic focus. For Germany, the flying bomb was a masterpiece of wasted potential. It was the brainchild of brilliant engineers pressed into service for a desperate dictator, creating a weapon that consumed scarce resources far faster than it achieved measurable military results. It was the ultimate weapon of reprisal, costly to create, yet fundamentally incapable of delivering the knockout blow that the Nazi leadership desperately craved. The V-1 was not a war winner. It was merely an expensive, noisy footnote in the final agonizing months of the Third Reich. But the noise did not die completely. While the final V-1 launch sites were overrun and silenced by the Allied advance in early 1945, the ideological and engineering blueprint of the weapon proved far more resilient than the regime that created it. For the victorious powers, the remains of the V-1 program, the captured airframes, the disassembled Pulsejets, the complex yet elegant guidance mechanisms, were not just wartime salvage, they were the technological spoils of the future. The Allies immediately recognized the strategic implications of the flying bomb. It was a crude design, but it was, without question, the first true operational cruise missile. The American military rapidly reverse-engineered captured components to create the JB-2 Loon, which was essentially a direct, slightly enlarged copy of the V-1. Though the Loon never saw combat, it served as the critical foundational platform for American post-war missile development, validating the concepts of ram air navigation and unmanned strategic delivery. Similarly, the Soviet Union studied the V-1 intensely, integrating its design principles into their own early cruise missile projects, establishing a precedent that would dominate strategic planning throughout the coming Cold War. The V-1 had proven two profound, immutable principles that would define the next century of aerospace warfare. First, it showed that an expendable, mass-produced airframe could deliver lethal firepower hundreds of miles away without risking a highly trained pilot. This changed the economic calculus of bombardment forever. Second, and more importantly, it demonstrated the viability of autonomous navigation. While the V-1's accuracy relied on simple gyroscopes and an air log that counted propeller revolutions to estimate distance, it established the operational requirement for what would eventually become sophisticated inertial navigation systems and terrain contour mapping. The engineers who worked in the shadows of Peenemünde had unintentionally mapped the path for future weaponry. They had created the progenitor of every Tomahawk, every Exocet, and every stealth cruise missile currently deployed across the globe. Modern missiles use turbojet engines rather than the temperamental Pulsejet, and they employ GPS and laser guidance instead of compressed air and counting turns. But the fundamental profile remains unchanged, an unmanned winged aircraft flying low to evade detection, programmed to strike a precision target hundreds or even thousands of miles from the launch point. The V-1, the weapon of desperation and terror, ultimately failed its primary mission of forcing British surrender. Yet, in failing, it succeeded in ushering in a revolutionary new category of warfare, closing the chapter on traditional manned bomber fleets and opening the era of robotic, long-range power projection. The noisy, inaccurate doodlebug of 1944 was not the culmination of a failing war machine, but the foundational blueprint for the guided missile systems that would dominate international military strategy for generations to come.